So it looks like people have started to find the Hangout that's actually working. Sorry about that. I was having some trouble with the Q&A function on the original one, and it seemed easier just to create a new one. Thank you for coming today. Today is going to be the first workshop in the series on power analyses. So it's going to be kind of an introduction. It's going to give a little bit of justification behind power analyses, some basic ideas about where to get effect sizes, going over some potential problems with different sources of effect sizes, and start to give you a few practical examples of using two specific types of software, R and G-Power, to do power analyses. In later workshops, we'll cover more complicated topics like simulations and bootstrapping for power analyses, but this is kind of the first introduction. So I wanted to, before we start, just wanted to go over how you can ask questions during the presentation. So if you join the Hangout through a Gmail address, you should see a Q&A function on the side of the screen where you can type in questions. So for people who did sign into a Gmail address, can you, is the Q&A function showing up? Does somebody want to just like type in a question and see what happens? All right, all right, so I'm not sure if anybody just tried to type in a question or not. Nothing's showing up, so I'm guessing nobody tried. But if you joined with a non-Gmail address, you can't actually use the Q&A function. But the workaround that we're going to use is I have my email open up in another window. So if you send questions during the presentations to Courtney@cos.io, they'll show up in my email and I can answer them that way. Yes, okay. Yes, thank you, Shauna and David. The Q&A seems to be working for those of you who have Gmail, so you can ask questions that way, or if you did not sign in with the Gmail account and you're just watching this in streaming, you can send questions during the presentation to my work email. They'll show up and I'll answer them that way. And then after the presentation, if you have any follow-up questions, you can send emails to stats-consulting@cos.io. So just wanted to go over how to interact during the presentation, and now we'll go ahead and get started with the actual content. So as I mentioned, I'm kind of going to go over four main things: what power is, why it's important, some nuts and bolts of how to do power analyses using R and G-Power, and then also talk about some practical considerations for power analyses. So what is power? Some of you may know this. A lot of you probably do know this, but just to make sure that everybody's on the same page, I kind of want to go over it just quickly. So power is the probability of rejecting the null hypothesis when it is false. So let's say you're running a study and you're looking at whether there's an average height difference between men and women. Your null effect or your null hypothesis is there is no difference. So because we know there is a difference between men and women in height, the null hypothesis is false. So power is the probability that when you run your study, you will find a significant difference in height between men and women. Right, so given a real effect, what is the likelihood that an experiment will yield a significant result? So 80% power means that you have an 80% chance of getting a significant result when an effect is real. So going back to my example, if I ran 100 studies looking at height differences between men and women, and I had 80% power in each of those studies, that would mean that 80 of those studies out of the 100 would show a significant result. And so the power of a study is based on a couple things. So it's based on the effect size that is out there in the population. It's based on the sample size you have in your study, and it's based on the alpha level that you choose. So in some disciplines like psychology, there's a default alpha level, p is equal to 0.05. In other disciplines like physics, the p-value is set at a different place, and some disciplines actually have a little bit of flexibility in what that p-value is. So they may often use p is equal to 0.05, but sometimes they may use a p of 0.1 or a lower p-value, depending on the study. So those are kind of the three main variables that go into determining the power of any individual study. So why is power important to me as a researcher? Well, it's important for a couple of reasons, but the main thing is that power tells you how likely you are to detect real effects. So, if you run a study and the effect really is out there in the population, how likely is it that you will find a significant effect? So, just to give you kind of an example of how low power can be a problem, in psychology, which is the discipline I originally come from, the power of a typical psychology experiment is 41%. So what I mean by typical is that some researchers took the average effect size in psychology. They got this from a meta-analysis. And then they looked at what the typical sample size is, which is generally 20 people per cell. And when you take those two things into account, you get a power estimate of 41%. In other disciplines like neuroscience, some studies have shown that the median power is 31%. So there's evidence from a variety of different fields that in a lot of empirical studies, power is quite low. But let's take the example of a study that has 41% power. So if you run a study and it has 41% power, that means that you're going to miss a real effect 59% of the time. So if you run your study looking at the differences between men and women in height with 41% power, and you draw 100 samples, only 41 of those are going to show a difference. 59 of them are going to show that there's not a significant difference between. And so what that means is that you're putting in a lot of experimental resources into studies that are not likely to show you a significant result when that effect is real. And so you're kind of sinking a lot of resources into studies that have a very low chance of succeeding. Now, that's for one individual study. What about the case where you found a significant effect once and you want to replicate that effect in a second study? Assuming that both studies have 41% power, you're only going to have a 16% chance of finding that result both times. So that 16% number comes from the fact that these are two independent events. And so probability theory tells you that the probability of two independent events both happening is multiplying the probability of each of them together. So if each has 41% power, the likelihood of finding both of them significantly is 16%. So this is really, really low, right? And so the problem is that running low-powered studies, in the long run, you end up sinking a lot of resources into studies that aren't going to show significance, not because that effect isn't really out there. The effect many times may actually be out there. You're just not finding a significant effect because your power is too low. And so you're not actually getting much useful information out of the studies. So, why is power important to me? Well, the more high-powered studies you run, you're actually going to find a larger number of significant results because you have a better chance in any given study of finding a significant result because your studies are properly powered. And as I mentioned, it keeps you from wasting resources. It does generally require a greater investment up front, but because you're getting more information out of each study, it's less wasted resources over time because you're less likely to, run a bunch of studies that get null results when you could have been tapping into something real and finding significant results. So how do you actually go about doing a power analysis? Now, the exact way you do it obviously will depend on the the type of study you are running and the type of statistical test you're doing. But at a general abstract level, the process is kind of the same for any study. So generally, we as scientists want to be running a priori power analyses. So these are power analyses that are done before data collection has started in order to determine how many subjects you need to run. This is subjects or mice or samples, whatever. I usually work with human subjects, so I default to subjects. But if you do biological research, many times your subjects are mice or they are samples of cells or something like that. But the point of the a priori power analysis is to tell you how many subjects you are going to need to run to achieve a certain level of power for your study. And so what you'll need in order to run an a priori power analysis is a couple of things. First, you're going to need your analysis plan. You need to know exactly what statistical test you are going to run. And so by that, I mean the type of test. So are you going to be running a regression? Are you going to be running an ANOVA? Are you going to be running a t-test? And you also need to know the exact setup of that test. So, if you're running a regression, you need to know how many predictors are going to be in that regression to run a really informative power analysis. You also need to have some estimation of the effect size of the effect you're looking for. So if I want to run an a priori power analysis to figure out how many people I need to run to see if there's a difference between men and women, I need to have some sort of guess about how large the difference in height between men and women might be. Another thing I need to know is what is my desired level of power? So there's kind of a range of levels that some areas of science have deemed acceptable power levels. So in medical research, 80% power is kind of the lower bound of acceptable power. 95% power is ideal. Ideally you have 99%, but generally that requires insanely large samples. So, 95 is the ideal, 80% is the lower bound of acceptable. So oftentimes people will run sensitivity analyses where they look at 80, 90, and 95% power and see what the sample size requirement for those three levels might be. And the last thing you'll need to know is what alpha level are you going to use. So in many fields, as I mentioned, an alpha level of 0.05 is the convention, but that's not the case for all fields. And some fields have a bit of wiggle room in their alpha level. So you can move the alpha level around and that will change the required subjects. So I think the most complicated thing with power analyses is figuring out where to get effect size estimates. There are a bunch of different places and different locations for getting effect sizes have different pros and cons. So the first place to potentially get effect sizes from is meta-analyses. Meta-analyses are a great place to get effect size estimates from because they aggregate across a large number of studies. And so you generally get a more stable estimate of the effect size. Because you take information from many studies, you can get kind of a better estimate of what that effect size might be out there in the population. Many meta-analyses also will look at moderating variables. And so depending on how you're setting up your study, the meta-analysis may tell you that you are likely to have a smaller or larger effect size than another study on the same subject that was set up in a slightly different way. And so you can get a lot more information about what your effect size might be. Now, meta-analyses have not been done on every single area of research, so a lot of times a meta-analysis isn't available. So another thing you can look for is similar studies that have been done previously in the literature. So the more studies you can find, the better, but even one study is going to give you some information. So the thing to consider with this is that power analyses can be very, sometimes, not always, the effect size of a phenomenon can be very sensitive to how the study is set up. So different DVs may yield different effect sizes because they are more or less sensitive to the manipulation. And so when you're looking for similar studies, you want to find studies that are as similar as possible to the one you're going to run, because that's more than likely going to give you a better estimate of the effect size you're likely to get. So another possible place to look for effect sizes is an exploratory pilot study. So if you have absolutely no idea what your effect size is going to be, there's no meta-analysis, no similar studies have been done in the literature, what some people will do is say, okay, I'm going to run 20 people and look at what the effect size is in that small population and use that as the estimate of my effect size. The problem with this is that effect sizes from smaller populations, especially significant effect sizes from small sample sizes, tend to be inflated. And so the exploratory pilot study is actually probably giving you an effect size that is too large. And so if you use that to power studies going forward, that can be a problem. So something else that people have suggested for cases where you really have no outside information about what your effect size might be is to take a guess. And this is an educated guess rather than just a shot in the dark. And so there are kind of two options. One is to use the average effect size. So some disciplines have done meta-analyses looking at what the average effect size is. So I mentioned that there was a meta-analysis that looked at the average effect size across social psychology. And I believe the average effect size is a Cohen's d of 0.3. So that can be a place to start if your particular discipline has done some research looking at the average effect size. Another great option is to think about what is the lowest meaningful difference that you care about for your study. So if you're running a study and you really have no guess what the effect size might be, but you think through, okay, what is the lowest effect size that I would deem substantively significant? So for example, if I'm looking at a height difference between men and women, I might determine that, if it's only an average height difference of an inch, that's not really substantively significant for me or for the research I'm doing. I'm only really going to care about a difference of, let's say, 3 inches or greater. So I can use that 3 inches or greater to power my sample size so that I have 80% power to find a 3-inch difference between the groups. A lot of times, rather than thinking of this in absolute units, people will think of this as small, medium, and large effect sizes. So they'll think, okay, I want to be able to find a medium effect size or larger in my study. So I'll look at the conventions for Cohen's d that show that 0.5 is considered medium, and I'll power it off of that. Or somebody else might say, well, I actually really do care about small effect sizes. So I'm going to power under the assumption that I have a small effect size here. So I wanted to quickly go over some kind of practical ways to do power analyses before I started getting into kind of the nitty-gritty of more considerations about effect sizes. So depending on the software you use, there are different ways to do power analyses. So if you're a person who likes to use SAS, there is a proc power function in SAS that you can use that will do a lot of power analyses for you. I'm not going to demo SAS today just because I don't currently have a SAS license, so I cannot demo it for you, but I am going to do some demos of R and G power. So for R, depending on how much you know about it, there are many different libraries that are created by independent users. So there is one particular library called Power, PWR, that does power calculations in R. However, there are a lot of other power calculation functions that are kind of spread out throughout the different libraries in R. For example, there's a particular function that will run power analyses for Sobel tests in R. It's not in the power library because it's so specific. It's in a library for running Sobel tests. So generally, if I go to do a power analysis in R and it's not in the power library, I'll start Googling to see if I can figure out if somebody has actually created that function in some other package. But the power library is a great place to start. So I wanted to kind of show you how that works. So I'm going to switch screen share for a moment. Here we go. Okay. So for those of you who may be less familiar with R, what you're seeing on my screen right now is something called R Studio, which is a very nice way to kind of interact with R rather than just through the main R console. So I still have my console down at the bottom left, but I also have a script on the upper left where I can save code that I've written. And I also have some information about packages that's going to come up in the bottom right. So, you know, if you're thinking about getting into R, I would highly suggest downloading R Studio rather than just the normal R console. It makes your life a lot easier, especially once you start doing a lot more coding with R. So when you open up R, the Power package doesn't come preloaded in it. You have to install the package. Mine's already installed, but you would say install package, and then you would say Power. If you ran that, it would install it. Can you actually read what's going on in my console, or do I need to? It looks like it would help if I increase the size of the font, or is it good on your all screens? That might just be how big the window is on my computer. Okay, no, that actually does look readable. All right, so now if you are interested in figuring out, okay, what does this package do? If you go into the bottom right function, you can actually click on Power, and it'll give you all the documentation for what that particular package does. So if you'll notice, it has a bunch of different things it can do. It does your basic chi-squares, tests of proportions, t-tests, generalized linear models. So it does a lot of the basic stuff. One thing it doesn't do is really more complex design. So it's not really going to give you power estimates for things like mixed models or logistic regressions or higher order ANOVAs. But for basic tests, it will do them nicely. So just to show you a t-test, so if you click on that, it shows you how to use it. It shows all the inputs at once. So if I want to determine what the power for a t-test is, I'm going to type in power.t.test. I want the program to give me the number of people I need. So the n is equal to null. That means it's asking the computer what is the necessary n. So I'm going to assume that I have a medium-sized effect, so a Cohen's d of 0.5. I'm going to set my significance level to the general level for psychology, so 0.05. And I want to have 95% power in the study. And then I have to tell it the type of t-test I want to run. So I want to run a two-sided test. And then I also need to tell it what type of hypothesis test I want to run. So do I want to run a two-tailed test or a one-tailed test? And I'm going to run a two-tailed test, which is two-sided. So if I type all that in and I hit enter, okay, so I mistyped something, of course. So type, I put two-sided, that should be two sample. Right, so this will run, one sample p-test, two sample p-tests, or paired sample t-tests. So now that should all be, okay, right. And so what you see is it spits out the number of people I need. Now note at the bottom it says n is the number for each group. This is just something to keep in mind. So if I wanted 95% power for a 2-sample t-test with a medium effect size, I would need basically 105 people per condition, which would be 210 people overall. So one other thing I wanted to mention, because it's been coming up in a lot of email questions I've been getting recently, is power analyses for ANOVAs. So I mentioned that the power library has an ANOVA function. If you look at it, it's specifically the it's specifically for a one-way ANOVA. So this will not do factorial ANOVAs with interactions. This is just something to keep in mind. In R, a lot of times when you get more complicated designs, you have to start doing simulation-based power analyses. We're going to talk about those in later workshops. R is great for doing simulations, but because a lot of the power analyses are run-off simulations, some of the just basic functions aren't necessarily built in, or they're harder to find. So if you do power calculations in R, you should make sure that you're aware of kind of what type of test it thinks you're running. So if you had, a 2x2 ANOVA and you put in number of groups as 4, it would think you're running a 4x1 ANOVA. And so you would actually get an incorrect N for your power calculations. So that's kind of how you run power calculations in R. Before I move over to G-Power, does anybody have any questions about that? Okay, yeah, so as I said, the intro lecture is just to kind of give you some information to dip your toes in. Obviously, this is not a comprehensive of everybody do power calculations in R, but hopefully this gives you some ideas about how you might be able to start. One reason to potentially do power calculations in R rather than something like G-Power is because you can save this syntax. So if I had actually written this up into the script above, I could save this and for later use. And so I could go back to it, I could save it into the syntax for my entire study, things like that, which a point and click program like G-Power does not allow you to do. So now I'm going to go ahead and switch my screen to G-Power so I can go through that. So here we go. Okay, so G-Power is a point and click program. It's completely free. It's through the University of Dusseldorf. So if you just Google G-Power and Dusseldorf, it'll take you to their website where you can download both the program and there are 2 PDFs. One is a tutorial and one is a user's guide. I don't generally like reading user guides. I don't think anyone does, but their user guide is actually pretty useful and pretty readable. They have more support for some types of tests than others. So for example, they have some nice walkthroughs of how to do things like t-tests and between subjects ANOVAs. Their walkthroughs for anything related to regression, so logistic regressions, multiple regressions, it's out there. It's less reader friendly. And the support for within subjects designs is actually really lacking. So I did want to go over some kind of peculiarities of how G-Power does that, because that's come up in a lot of questions I've gotten over email. But just to kind of show you that G-Power and R are going to give you the same results. So the way G-Power works is it has a bunch of different test families. So what you'll notice is that G-Power appears to be far more extensive than R in the types of tests it will do. So for t-tests, it has a ton of different types of tests. Same thing with f-tests. It'll do ANCOVAs, ANOVAs, MANOVAs, And then it also has some tests for chi-squares, and then some exact tests if you're interested in proportions. So it has a lot of options out there. So I'm first going to just show you the exact same t-test we did before in R. So t-test, so I'm looking at means, and here I want two independent groups because that's what I did before. So G-Power offers a couple of different types of power analyses. A priori is generally the one that you're going to default to if you're trying to figure out the sample size you need. But for example, let's say your sample size was fixed because you only had so much money from a grant, or you could only find so many patients with a particular disease that you were interested in studying. You might be interested in, given a certain sample size, a certain level of power and a given alpha, what effect size would you be able to detect? Then you would want to run a sensitivity power analysis. But a priori is generally what you're going to want to be running. And so then each different test has different inputs. You could choose either one-tailed or two-tailed. I happen to know what my D-score is, but for pretty much any test, you can click on this determine, and it'll give you some options for inputting other information to calculate what that difference actually is. So if I didn't know my D-score, but I had information about the means and standard deviations, it would calculate it for me, and then I could use that function. You put in your alpha level, you put in your power, and then this allocation ratio is just asking whether you, right, this is a t-test, so there are going to be two groups, whether you want an equal number of people in both groups, which I do. So then you click calculate, and then it'll tell you, what the number of people in each sample is and what the total sample needed is. So if you notice, this is giving me the exact same answer as I got in R, 105 in each group for a total of 210. So, usually no matter what program you use, you're going to get to the same result as long as you're running the same test in both. So I mentioned that G-Power has some quirks for within subjects designs, and I did want to mention these just because the information is a little bit hard to find out there. And I think in a lot of disciplines, a lot of people run within subjects designs because they generally give you more power. So if we go over to F-test, ANOVA repeated measures, what you'll notice is that there's this little option button on the bottom. If you click on this, what you find is that there are different effect size specifications that G-Power allows for within subjects designs. And the reason is that there are different ways you can calculate effect sizes for within subjects designs. In general, so if you're an SPSS user, obviously you want to use the as an SPSS option. But you may actually want to use this option even if you don't use SPSS. What this option is telling G-Power is the effect size you're going to give it already takes into account the correlation between those within subjects factors. So, so what you'll notice is that I'm not asked for a correlation when I choose this option. So in general, for ANOVA's partial eta squared is the effect size that people report. It's the effect size a lot of times that you're going to put in. What that as an SPSS option means is that this partial eta squared already has that correlation built in. So the partial eta squared you get from SPSS has that correlation built in. If you calculate your partial eta squared as using the sum of squares effect and the sum of squared errors from the F output, it's already going to have that correlation built in. And so that's why I mentioned that even if you don't use SPSS, you may actually want to use that option. So one way to kind of figure out if the partial eta squared you have takes into account that correlation or not is actually calculate that partial eta squared by hand using that SS effect and SS error and compare it to the partial eta squared the program you're using is spitting out. If they're the same, then that correlation is already taken into account, and you want to use that as an SPSS option. This option is hidden. Not a lot of people realize it's out there. And so depending on which of these you choose, the same effect size will give you very different total sample sizes. And so that's why I wanted to make sure everybody's aware of that. The other thing to mention about how G-Power, or an assumption that G-Power is making about ANOVAs. So I mentioned how the power.ANOVA.test in R tells you that it's assuming you have a univariate or a one-way analysis of variance. G-Power makes some assumptions about your ANOVA designs as well, but it doesn't tell you that. So this ANOVA repeated measures within factors, right? It asks you for the number of groups, which if you have a cross design if you have a mixed design, but you're only interested in the within factor, that's what that number of groups is talking about. It also asked you for the number of measurements. This is assuming that you have one within subject's factor. It can have as many levels as you want, but if you put in 4, it's assuming that that is a 4x1 within subject's factor. If you have a 2x2 within subject's design, and you put in 4, because technically the number of measurements is 4, the program thinks you're running a very different setup of a test than you actually are. And so you want to be careful about how you put in the number of measurements and the types of designs you use this for. Similarly, this within between interaction for repeated measures designs. So that also has that as an SPSS option. But similarly, the software is assuming that you have one between subjects factor and one within subjects factor. And so you would have a 2x4 rather than, a 2x2x2. So that's something to keep in mind when you're using G-Power. It's something that is a little tricky to figure out, and it's not well documented. And so I did want to make sure that everybody was aware of that, because it can get you into some problems if you don't realize that the program is assuming you're using a specific type of ANOVA and your design actually isn't looking like that. So that's kind of how you use G-Power. As I said, there is pretty good documentation for a lot of the tests. After the workshop, I'll put up a link to where you can find all those PDFs, as well as some other good online resources for using G-Power. Before I go back to talking about choosing effect sizes and sensitivity analyses, does anybody have any questions about either R or G-Power in terms of general use for power calculations? Okay, great. So I'm going to switch the screen share. Where's my mouse? There it is. Oh, come on. There it goes. Okay, so back to the presentation. Right, and so as I said, I'll post this link and some links to other resources for G-Power and R after the presentation. So, oh, no, looking at the wrong thing. Okay. So, now that I've kind of gone over some basics of some of the software you can use and places you can get effect sizes, I did want to talk about things to consider when you're doing your power analysis, because power analyses are surprisingly complicated, and a lot of times there's no one exact right answer for the number of subjects you're going to need to run. Usually you can find a range. And so how do you take that information into account? So the first thing to consider when you're doing a power analysis is available lab resources. So obviously we all want to run well-powered studies, but we only have so much money, so much time, and so many participants. And so if it's the case where you know that you can only run, let's say, 200 people for a particular study, that's really important information to have. It doesn't mean that you shouldn't do a power analysis. You should probably still do a power analysis, because let's say you were running a really complicated, 2x3x4 design or something. As I mentioned, I come from psychology. We really, really like our higher order interactions. So let's say you're running this really complicated design. You only have 200 people, but your power analysis is telling you you would need something like 400 people to run that study with adequate power. That's actually really useful information to know. And so kind of being aware of how many lab resources you can devote to a particular study is actually informative, because when you run the power analysis and it's telling you you need a lot more people, that may suggest to you to potentially change up some things with the study. So for example, you can think about ways to increase power without needing to have excessively large sample sizes. And so there are a couple of ways to do this. I think increasing sample size to increase power is the thing that most people initially think of when they think of power analyses, but it's not the only way. So what are some other ways to increase power? So the general idea is that anything that increases the mean difference between your conditions or that decreases the variability within groups will increase your power for a given sample size. And so what you can think of is, if you're doing experimental work, you can try and choose stronger manipulations. So there's generally more than one way to manipulate any construct. Some manipulations are stronger than others. A good way to look at this is to look at things like meta-analyses, to look at previous studies that have used different manipulations. If you're working in an area that you have a lot of previous research in, you probably have an idea of which manipulations are stronger than others. And so you can use those stronger manipulations if you don't have a lot of lab resources to devote to a particular study. Something else to consider is using more reliable measures. So more reliable measures are going to decrease the noise in your sample, and so you're going to get stronger power. So once again, a lot of times there are different ways to measure any particular construct, so you have a bit of choice. And so you can look to either work you've done, work that other people have done, to see, okay, what is the reliability of the different possible measures I can use? And so you can move towards this more reliable measures. Another thing you can do is use theoretically relevant covariates. And so I want to stress the theoretically relevant part of that sentence. So for example, if I'm looking at the difference in height between men and women, there might be some covariates which are theoretically relevant to that height difference. So, but are probably going to soak up some noise in my data. So I might want to put in things like parents' height, or country that the person was born in, or information about how much access they had to good quality nutrients when they were growing up. These are all covariates that I could put into my model that are very theoretically relevant. I would specify them beforehand, but because they're theoretically relevant, they're probably going to soak up some noise in my data and make it easier for me to find that effect I'm actually looking for. And so these are some things to consider when you're designing your study. Right, and so another thing you can do is actually think about what specific statistical model or method you're using. So different statistical methods and models have different, some are more powerful than others. So, you can think about whether you want to use a one versus two-tailed test. You'll have more power if you use a one-tailed test. Obviously, you're only going to want to use one-tailed tests in a situation where you really have a strong reason to hypothesize that an effect will go in one particular way, but that is an option. Another thing to think about is within versus between subjects designs. Within subjects designs generally have far more power than between subjects designs. Obviously, not all experiments can be run within subjects. Sometimes that does create some problems, but it's always a good option to think through if a between subject design is just needing too many participants and you can't get that number down, it's a good thing to consider. Right, and so I talked about available resources, ways to increase power without having to run huge samples. So another thing to consider, and I kind of foreshadowed this earlier on, is the accuracy of your effect size. So as I mentioned, depending on where you get your effect size from, your estimate is going to be more or less accurate. So just to give you kind of an example of this, the question is, well, how accurate are our effect sizes? So because there's a lot of publication bias in the literature, and because in general, the studies many scientific disciplines tend to run are underpowered, this can lead to inflated effect sizes being published in the literature. And so this is a problem because if you use those inflated effect sizes to determine your power, you're not actually going to have as much power as you think you have. And so this is a graph from Yuri Simonson's Data Colada blog. And so what it shows is how much power you think you have and how much power you actually have. This is assuming that the original study had 50% power, and you're using that to do another power analysis. And so what you'll see is you can think you have 80% power, but only have something like 51% power, which is a problem. And so what are some ways to kind of deal with the possibility of inflated effect sizes? And then how can you make more informative choices about your power analyses? And so another thing to keep in mind is our effect size estimates are point estimates. They're not the true population values. And any study is going to have some uncertainty around the estimate it gives you. So all effect sizes have a point estimate, and they also have confidence intervals, which tells you kind of how it tells you the amount of uncertainty that surrounds that particular point estimate. Some estimates have really small confidence intervals, which tells you that there's more certainty about where that point estimate lies. Some have huge confidence intervals. So if you're using a previous study that had really wide confidence intervals, and you're only using that point estimate, the true effect size actually may be a lot smaller than you think it is. It might be towards that lower bound of that confidence interval. And so taking into account that uncertainty around a particular effect size can be really useful in terms of trying to get a more informative power analysis. Right. And so, okay, we are running a little short on time. I kind of already went over this. Right, so just to give you an example of how this works, here's an example study where it had a point estimate effect size of 0.8, but it had a pretty wide confidence interval all the way down from 0.22 to 1.37. If you run an 80% power calculation on the lower bound, upper bound, and that point estimate, what you'll see is you get a huge range of possible required sample sizes for that power analysis. So then the question becomes, okay, well, there's this huge range. One of them requires, 650 people, which is a lot, and one of them requires only 20. How do I use this information to actually pick a sample size? And just a side note, studies with larger n's will have smaller confidence intervals. So, right, what is the well-meaning researcher to do? You want to do a power analysis, you want to do it well, but you're like, well, the effect sizes are probably inflated. There's this huge range. What can I do? So there are two suggestions that some people have put forward. One is the 2.5 rule, which is suggested by Yuri Simonson. And the idea is, his idea is basically, we know that a lot of the published effect sizes are inflated. So replication should just use 2.5 times as many subjects as the original study across the board. Another suggestion comes from a paper It's called Safeguard Power. There was a really nice paper about this in the May special issue of Perspectives on Psychological Science. And so the idea behind this is, rather than just have an across-the-board rule, is to actually take the information from the confidence interval into account when you're running your power analysis. So what Safeguard Power is it calculates power based off the lower bound of an 80% confidence interval around that original effect size. So depending on how wide the confidence intervals are, that lower bound may be farther or closer away from that point estimate. And so just to give you an example comparing the different methods. So these are 4 studies. Here is the effect size for the original study, the original N, and then the power estimate using three different methods. Power N is just running a normal power analysis. There's Safeguard N, and then there's that 2.5 rule. And so what you'll notice is that when the original study had a really large N, the normal power calculation and the safeguard power are a lot closer together. That 2.5 rule gives you a huge estimate. However, when the original sample was smaller, the safeguard power and the 2.5 power tend to look more similar, and they're generally larger than that original power number. So you may be asking yourself, okay, what do I actually do? So one good thing whenever you're running a power analysis is to actually run some sensitivity analyses. So look at what the normal power calculation gives you. Look at the safeguard power. Look at the 2.5 rule. Take into account what the original sample size was, right? A larger original sample size is going to have smaller confidence intervals. It's going to have a better estimate of that original effect size and be less likely to inflate it. And so in that case, going with that safeguard power estimate is probably fine. You probably don't have to go for this really large 2.5 N rule because this estimate is less likely to be inflated. But as that original sample size gets smaller, you may want to go more towards that 2.5 rule. But once again, you do have to weigh these with feasibility considerations. So it's not that there's always one correct answer. A lot of times it's about getting the different pieces of information about the different applications, taking that into account, taking into account feasibility considerations. So getting as much information as you can and then weighing the pros and cons. Right, so what should you do? Right, rather than running an individual power analysis, it's really about running a series of power analyses to see what the possible range of sample sizes is, and then make decisions based both on power considerations and available resources. And just a note, we'll talk about this in future workshops, but a really nice thing to do is actually combine power analyses with other methods like cumulative meta-analyses and sequential analyses, so you can actually optimize your power and optimize your available resource use. So for example, let's say for this slide, in this one, you had gone with safeguard power, which is requiring a huge number of subjects, but this effect size actually wasn't all that inflated. This was actually pretty close. If you just ran this number, you would run a ton more than you needed. Sequential analyses are a way to peek at your data without inflating your type 1 error. That could kind of help you guard against accidentally running too many people. So the last thing I wanted to say is just a quick recap. So why do power analyses? A properly powered study will result in more significant effects. It will lead to fewer unnecessary abandoned lines of research and will give you more certain estimates of your effect size, which will help future researchers run more properly powered studies. And so all these taken together means that in the long run, properly powered studies are actually going to save you resources. I did want to mention two things. The material for this workshop, so the slide deck, some PDFs about using G-Power, some resources about that, as well as the YouTube video that has been recorded for this, are all available at this website. It's an OSF project. So if you look at the OSF, I think the title is COS Statistical and Methodological Consulting. Or if you search for my name, Courtney Soderberg, it'll come up as well. So for all of our online workshops, the material will be posted after the workshop. There's another one of these in the afternoon, so everything will be posted after the afternoon workshop. So you can always go back and look at this material. And in addition, if you have any questions about what we've gone over today, or when you start trying to do power analyses, if you run into questions, you can always send us emails to this address, stats-consulting@cos.io, and I will be more than happy to help you out with your particular problem or answer any questions you might have. So that is the end of what I had. Thanks so much for coming this morning or this evening, depending on which continent you're on. And if you have questions, I can either answer them now, or you can email them to me later on. So thank you.